Good morning, all of you. My screen is visible. Anybody can? Hello.
Yes, sir. It is visible.
Yeah. Thank you. So, design of snubber circuit. We'll see today's class. We start with previous class. There is a protection of SCRs and all. In that, one of that is a snubber circuit design. Why we required this snubber circuit? Normally, to prevent dV by dt triggering, we use as a snubber circuit. In the previous protection, we noticed that for di by dt, protection is used to prevent the high current. There is an inductor used in series with the device so that we can minimize the di by dt protection. Similarly, to prevent dV by dt triggering, we used snubber circuit. So, snubber circuit consisting of a series combination of resistance, that is Rs, capacitance Cs in parallel with the thyristor. So, as I mentioned in the previous class also, normally there is a thyristor like this, and what we do is there is a resistance and capacitance are connected in parallel with the thyristor. So that's what, but these two are in series. There is a resistance Rs, this one is Rs and this is a Cs. So these two combination, that is a series combination of this portion I call it as a snubber circuit. So that is the why we are using as a snubber circuit is to limit dV by dt triggering. So that is our purpose. Next one. So normally in that case, to limit dV by dt, we required only capacitor is sufficient. But why that resistance is required, that also we'll see. Now, when the supply is given, sudden voltage appear across the capacitance. Now that will behave as a short circuit. Therefore, voltage across the device is 0. That is the way we are preventing the dV by dt triggering. So, if capacitor is not there, if you give supply, then what will happen? Rate of change of voltage will rise. That voltage is directly applied across the anode and cathode. Therefore, high voltage will be there across the device. There is a chance of getting more than the rated voltage. Rated means dV by dt voltage. In that case, junction J2 will be breaks down, device will start conducting. To prevent that one, we are using as one capacitor across the device, so that once if we give the voltage or switch is closed, then automatically the capacitor will act as a short circuit voltage is very small or 0 is equal to the same as the voltage across the switch. But later on, the capacitor is gradually charging. So that voltage now is parallel with the device only. So gradually capacitor is going to be charged. But our intention is to minimize the what we call it as voltage across the device initially, means higher voltage means dV by dt should not be more than the specified. So that is the reason we can say that. But now what will happen, because of the capacitor, that voltage will be minimum or 0 initially, then gradually it will develop. Then the CS will build up slowly and dV by dt across that voltage is same as that of a across the SCR. That obviously less than the dV by dt of the device. Hence the question is now what we observed is one capacitor is sufficient to minimize or to prevent dV by dt triggering. Then why resistor? because snubber circuit I drawn the previously, there is a series combination of resistor and capacitor in parallel with the SCR, that I call it as a snubber circuit. But as per explanation, one capacitor is sufficient to minimize or to prevent dVdt. Then why the RS, that is a resistance. So that is also one of the point. Now we can see here, this is our circuit. This portion I call it as a snubber circuit. As per explanation, capacitor is sufficient. The YRS, that is a high resistance, is in series with the capacitor is. Now we can see switch is closed. Then what will happen? Once switch is closed, this will be short circuited. Then voltage across this will be the zero initially. Later on, that voltage will be gradually rising. Then it will be within the limits. Now what will happen while this is charging, then you can see that plus and minus, that will be charged during off state, means switch is closed, the device is off, then the capacitor will be charged. Now what will happen, you can see, if we give the firing pulse to this device, then the device will start conducting. Once the device is start conducting, means it is on, then what will happen? Whatever energy stored in this, that is going to be dissipated through this. Let us assume that initially this is not there, resistor also not there. Now my question is explaining why the resistor, that's why. So now if no resistance, then if switch is closed, the device is going to start conducting. This current is passing through this device. Then what is the current? Because when the switch is off state, this is already charged same as the Vs. While it is discharging, the current, the resistance across this internal resistance is only there, but if you not place Rs, then the denominator is very, very small. This current is Vs by internal resistance. Now internal resistance is 1 ohm. This Vs is equal to the same as the current. That much current is flowing through the device. It is unwanted. That is the reason to limit this. Then what you will do is you can add one Rs, series resistance or a damping resistance, or that will be as a very high. Once if you use this high resistance, then what will happen? Denominator factor will be very high. Then automatically current will be minimum. That is the reason we placed as a series resistance. In the later classes, we will see that even by adding only the resistance is sufficient, but the problem is while it is recharging, it is there through the resistor. It's fine. But while it is charging, what will happen when the switch is closed? Then what will happen? That current has to pass the resistance while it is charging the capacitor like this, plus and minus, it is going through the resistance. Once the current is passing through the resistor, the dissipation is taking place, and charging time also it will take more. Tau is equal to RC, then that will be tau is equal to RC, no? So if R is very large, it will take more time to charge. So that is again there is a problem. To overcome that problem, we'll see the dynamic circuit under a series parallel operation moment. Yet moment, you can see that we are using as a snubber circuit like this. Then automatically we can suppress the dV by dt triggering, and if resistor is not there, high current will pass through that. That is the reason we are using as a large resistor to minimize the current. So that is our snubber. So now the design parameter, we need to find what is the value we have to place. Because I cannot put randomly. There is a to meet our requirement. What is our requirement? That is a dV by dt maximum they will give. in the specification. Similarly, di by dt maximum also is known to you. By knowing dv by dt and di by dt max, based on these values we need to design what is the L value and what is the CS, what is the RS. In fact, we required this also. You can easily find, because to minimize di by dt you need to place as a L. That parameters we need to find. One is the RS, another one is a CS, and L. So all these three parameters we can find. And one more, you can see that there is a one equation I have to write. What is that equation? Is when S is closed immediately. When S is closed, what will happen? Capacitor will close. Now we can write a voltage equation. So based on that, you can see that soon after the instant, I am not saying later time, the instant at which S is going to close, then automatically what is the voltage equation, or you can write KVL in that. So S is closed instant, you can see that this capacitor will be short circuited. Then what is else we have? We have only this resistance. This is the loop. You can see this current is passing like this. There is a source Vs. It go to Rs because this is the short. The moment switch is closed, then it goes to the inductor. Then RL like this to back. Then what is our voltage equation? I can write Vs, that is equal to Rs plus RL into I plus L di by dt. So this is our voltage equation. So Vs is equal to R into I plus L di by dt. That's it. So L is only one L and R is having some Rs and RL will be in series. Therefore, we can represent the drop Rs plus RL, that is a load resistor into I plus L di by dt. Now from this we can find what is the current I. So current I is equal to V by R, that is a Vs by Rs plus RL into 1 minus e power minus R by L into T. So now here R is a Rs plus RL. So into T by L. So now instead of writing that Vs by Rs plus RL, just I make it as a I. So that is only the representation. Simplified that I is equal to Vs by, normal formula is here, I is equal to V by R into 1 minus e power minus R by L into T. That is the expression for applying Laplace transform, inverse Laplace transform, or particular integral and complementary function like that. If we do, finally RL circuit excited by the DC supply, that is equal to current I is equal to V by R into 1 minus e power minus R by L into T. So R by L we can represent, there is a tau fashion also they represented, L by R is equal to tau. So just only for simplification, otherwise directly also you can use it. Now what I want is dI by dt. Now we can represent, as I know I is equal to this one, then you can just do the differentiation di by dt. So what is di by dt? I into this parameter is 0 and minus e power minus t by tau. So with respect to t, I can represent e power minus t by tau into 1 by tau. That minus and this get minus get plus, that will get cancelled out. So this is our di by dt. Now I know I v by rs plus rl into e power minus t by tau. So tau is here is 1 by tau is there. You can represent this fashion and automatically these two will get cancelled out, this one and this one, and finally di by dt is equal to Vs by L into e power minus t by tau. And the maximum di by dt max will occur the moment when the switch is t is equal to 0. Then you just substitute t is equal to 0 here. So e power 0 is 1. Then di by dt max is equal to Vs by L. So from that L we can directly get it. So this is the way we are deriving the what is the value of L. So now how much L value you have to place, that is based on what is the rating of the SCR, means what is the rating, di by dt rating. Another one is source. So what is source, Vs. That means we can represent Vs is equal to supply voltage. Based on supply voltage, based on the withstanding capacity of the di by dt, we can easily derive what is the value of L. Now we got the L value, that is equal to Vs by di by dt max. And what are the other parameters I have to find? Rs I need to find, as well as CS. So these two things we need to find. Now the switch is open condition. What is the voltage across that switch? VA into RS into I. Means voltage across the device is nothing but a RS into I. Because resistor is connected in parallel with that, and whatever current is passing through that, that will give as a drop. Now differentiate like what we did for I, no? Similarly, for voltage case, you differentiate this dV by dt, and Rs, that is a constant, I, that is a di by dt. Now I know what is the di by dt. That we can represent, you consider at a maximum instant, dV by dt max is equal to Rs into di by dt max. What is the di by dt max? Vs by L. You substitute that value. So this one di by dt max is nothing but a Vs by L. And if you know that Rs now dV by dt max is equal to Rs into Vs by L. So that will give as a dV by dt max. This one. And from this, what I can write Rs? This is simplification, L by Vs into dV by dt max. That is the Rs. That much resistance you have to place based on your rating of the dV by dt rating. And otherwise, you can see that RLC, what they will do is they are doing some trial and error, changing of the values, and finally they concluded one empirical relation for reliable operation. Then what they will do, Rs can be obtained from this relation. So this is the generalized expression we got from our analysis. But what, by changing this dV by dt and changing the inductance value, supply value, and they are finding that appropriate Rs value by doing trial and error, and without any large what you call it as derivation, they got one empirical relation by changing random values or trial and error procedure. And finally we got Rs is equal to 2 del root of L by Cs. The delta is a damping factor. The range is 0.5 to 1. In between any value you can take it. Accordingly we'll get it as Rs. That Rs will give as a accurate when compared to the previous formula. So now if I know Rs, you can easily find what is the Cs. This is the relation we got it, empirical relation, by changing R value, L value, and the input value, all these parameters, and they find one suitable solution for the Rs, that is equal to 2 del root L by C. Already we know what is the L. In the previous slide, there is a limiting inductor, or you can say that limiting di by dt, we calculated what is the L value. Now once if you know the L value, automatically Rs is equal to 2 del root L by C. Already L is known, and del we can define this value 0.5 to 1, and Rs will get it from this relation, and we can easily calculate what is the Cs. So this is the empirical relation I am telling. So now we can easily find what is the Cs from this expression. So now all the parameter Rs is known, Ls is known, and Cs will get it in this fashion. And optimal value, we can say, take it as a delta is 0.65, or you can say in the some cases in a problem also they will specify for this value of delta. If not given, you can choose your delta value or eta value. So we can say that 0.5 to 1. So within that any value you can take, but you must specify that value there and you can substitute it. So from that we'll get it as a CS is equal to, just square it both sides and we'll get what is the CS value from this. So now we'll see the one problem. The problem is mentioned here, a thyristor controlling the power in a load resistance RS. Because normal one thyristor, there is a load RL is there, we are able to control that through thyristor. The supply voltage is 240 volts DC, input side Vs is given, and the specified limits for dV by dt and dI by dt both is mentioned. For SCR, dI by dt is 50 amperes per microseconds and dV by dt is 300 volts per microsecond respectively. Determine the value of the dI by dt inductance and the Snubber circuit parameters RS and CS. So these are the three parameters we need to find. dI by dt inductance means L we have to find, and RS we have to find, and CS. These three parameters we have to find. Now you just given data is known to you. Vs is known. According to this, this is the Vs, this is dI by dt, this is a dV by dt. Now what we want is L, no? From this expression, L is equal to what? Vs by di by dt directly. Now L is equal to Vs by di by dt. L is known 240. Di by dt is 50 amperes per microsecond. Simply substitute that, we will get it as a, what is the value of L. So L is equal to 4.8 microhenry. Now, what is the other parameter we want to find? The RS and CS values. Now, RS formula is we derived already. RS is equal to L by Vs dV by dt max. So, L is known 4.8 microhenry, Vs is 240 and dV by dt 300. So, all these values are known. You can substitute here. We'll get what is the RS. That is a 6 ohms. And finally, we need to find what is the CS. So that will be empirical relation as I mentioned. RS is equal to 2 del root L by C or CS. That CS will be unknown. And del we have to choose value between 0.5 to 1. And therefore, for optimal value of delta is 0.65 they mention in the derivation. Otherwise, any one from 0.5 to 1 between you can take it and substitute the value of CS. So now you can get the CS value. So that is RS is 6, we got it, and 8.65 2 into and multiply L value. So that L is 4.8 into 10 to the power minus 6. So we'll get it what is the final CS. This is a simple design. And also important question, they may ask you to design this Snubber circuit and followed by problem. That is a complete essay question. So designing part, you can use source and let it be as a thyristor, in parallel resistor and capacitor, and in series there is a inductor and some load RL. So that is the simple circuit. You just design when the switch is closed, then capacitor will be short and write the KVL equation. Then you find the what is the current. After that you can find the dI by dt. From that we'll get it as L value. Then we can find the dV by dt from voltage across that switch, that is equal to R into I or RS into I, and just differentiate it and simplify that. Finally we'll got all the relations. Once the relations are known, they may ask followed by problem. Problem also depends on their requirement parameters. Sometimes they may ask all the 3 parameters, or sometimes any one also they may ask, depends. So that is only if you know the formulas of the Snubber circuit, you can get it directly. Design parameters. Now there is a other over voltage protection. What we discussed yesterday, some of the classifications of protections and all, and based on that Snubber circuit protection we discussed, that is the dV by dt and then dI by dt, all the things one by one. In that part there is a over voltage protection. It is most important protection scheme with respect to others. thyristors are very sensitive to over voltages. So this is one of the protection scheme, and then we'll see the over currents also. Maximum time thyristor failures happen due to over voltage transients. So the transient, as I said, no, there is a switching instance when the device is close or off state to on state or on state to off state, there is a transients is going to occur. That will be in our switching transients. There that may be subjected to the internal or external over voltages due to internal faults or internal case are due to external voltage. So we can see that internal over voltage after commutation of a thyristor. What is the commutation? Turn off process, we call it as a commutation. That means once the device is completely turned off, that we call it as a commutation. Reverse recovery current decays abruptly with the high di by dt. So because once the yesterday we seen the dynamic characteristics, when the current is zero, there is a negative voltage will appear across that device. So that is after commutation. There is the reverse recovery current. That means TRR and TGR I mentioned, no, to turn off that abruptly with high di by dt. There is a current also will drop down to remove the excess charged particles from the outer junction. In that portion there is high di by dt which cause high reverse voltage. That is the reason there is a spike will be obtained in the voltage across the device. That is the formula. We can see simple logic behind that statement. V is LdI by dt. Then what will happen? Di by dt is high because why the voltage also high I am telling. This VL is LdI by dt or switch voltage, and di by dt is high, then proportionality voltage also going to be large. That can exceed the rated breakover voltages. That is a once if the device I mentioned, no, what we call it as a voltage, you or you can say that thyristor want to fire, what we have to do? You have to apply one of the mechanism to trigger the device. In that case there is a voltage across the device is beyond the breakover voltage. There is a chance of break down the device, or the device may conduct, or if it is beyond that breakover voltage or VBO, it leads to the damage of the device. That is the problem here. V is large, that can exceed the breakover voltage or VBO, and the device may be damaged. So that is the problem for the internal over voltage if it's happened. And external over voltage, this can cause due to the various reasons in the like lightning or surge conditions. There is abnormal voltage spikes. So due to the source side, there is, if any abnormal voltage spikes will occur, that will leads as a external over voltages. And the external over voltage might cause different types of problems in thyristor. Operations like a increase in leakage current. This will happen, suppose the external over voltage will happen, that leads as increase in the leakage current. Then permanent breakdown of the junctions, unwanted turn on of the devices. So due to these reasons that will happen. So we must suppress the over voltages. So then protective measures, what we discussed, the over voltage causes, whether it is internally or externally, but that leads some problems, that also we discussed. And once if we know that, then what is the protective measures we need to do? That is the effect of over voltage can be minimized by using as a non-linear resistors. So that non-linear resistor operations, we can see that that will clamp the voltages. So clamping the voltage devices in the metal oxide uh, what we call it as varistors. I will show that device. You can see that you are connecting these resistors, or you can say that non-linear resistors. Once the voltage is beyond at that normal operation, if it offering high impedance, nothing but a open circuit. So in general, if no over voltage, all these things, normal voltage or normal system is operating, this metal oxide varistors will be open circuited, or you can say that high impedance that leads as a open circuit, and act it's not present in the circuit. So there is no impact because it is open. No, it will not be affect anything under open circuit if normal operating condition. Whenever voltage exceeds the rated voltage, then whatever abnormalities happen due to whatever may be the reason, then serves as a low impedance path to protect the SCR. So if it serves as a low impedance path, automatically it will allow the current pass through that is a high current. So automatically it will minimize the dA/dt. Then in turn the dV/dt also going to means voltage is going to be minimized. So that is the reason we are to use as a non-linear resistor. So that is the protection measure for the over voltages. Now we'll see the over current protection. So this will occur due to the different types of faults in the circuit. Like you can see that due to overcurrent, there is a loss, that is obviously I square R loss will be there, will increase the I generation of heat. If the I square R loss will increase the I generation of heat, may takes place that can be exceed the permissible limit and burn the device. So if I square is in the form of loss is in the form of temperature. So that will high, automatically that device will burn. And what we can do the protective measures? So SCR can be protected from the overcurrent using as a circuit breaker and fast acting current limiting fuses. So either of this we can use to minimize the what we call it as your protective measures. So circuit breakers are used to protection of thyristor against continuous overloads or against surge currents of the long duration, as circuit breaker has long tripping time. So here whenever the currents are high, we can make use of the circuit breaker to limit or to trip that system. But fast acting fuses is used because the circuit breaker time also is important. Our lab also we have circuit breakers by applying the fault, and we can able to see that how much time is take to trip that, because in the power system all the parameters are very sensitive parameters, and within a very no time or very small time we need to turn off the, or we need to isolate the system once fault is occurred. Now in our lab and power system lab also hardware experiments are there. We are intentionally creating the fault and we are checking how much time it will take to open, or you can isolate the system faulty areas. That also you can see it in our lab. And protection of SCR against high surge current or short durations. If, preferably we required as a very short duration. And another one is a high temperature protection, where we noticed this in the case of what you call it as turn on process. One of the method, as you are aware that there is a temperature triggering or a light triggering. How that is that will happen once the device is forward biased. Let it be anode is positive with respect to cathode. Then what is happening inside? Outer junctions are 2, inner junction is 1. So outer junctions are forward biased. If outer junctions are forward biased and J2 is not a conducting state or reverse bias condition, and what will happen? Very small leakage current, because both sides are open, very small leakage current will pass through the junction J2. So due to that small leakage current, then what will happen? Temperature will rise and that leads power dissipation. Again resistance of that junction will be dropped down, then it will allow more current, and this cumulative process finally temperature across that junction will increase beyond the specified temperature limit. So that is the reason once if it limits, then automatically junction J2 is going to breaks down. If junction J2 breaks down, automatically device will on without giving any gate signal or without any required the instant. You can just giving supply itself or forward bias condition itself, the device is turned on due to temperature. That's why to limit or to prevent this, we are using as a heat sinks, and it will observe the temperature. Observe the temperature. Then the temperature is within the limits. That is the problem. Same thing that will be applicable here also. That's only here we are explaining in terms of the protection. We can say that heat sinks is the protection, how the remedy and all. And before that, you can explain why the temperature will rise. That only I mentioned here slides. Some of the points. Increasing the temperature of a junction, you can see that insulation may get failure, and so we must take proper measure to limit the temperature rise. So the protective measures are, we can achieve this by mounting as a thyristor on heat sinks, which is mainly made by high thermal conductivity material like aluminum, copper and etc. So using this type of material, you are placing the device is placed over that metal or heat sinks, we can minimize. So mainly aluminum is used due to low cost, and these several types of mounting techniques that will be for the SER, such as lead mounting and stud mounting and bolt down mounting, because only the arrangement of heat sink with fitting of the device, we can see normally providing of the device in a heat sinks also there is a different phenomena. In the circular fashion we can make it, or you can keep the conductors. Here is one, here is one, here is one is different, or you can place the conductor, here is one, and let it be in this fashion. That will be also another problem. Symmetrical and unsymmetrical mounting, all this anyhow there is a series parallel operation case. We'll see that the different why we need to place the conductors in the symmetrical in nature. If not, what will happen, that will discuss at that series operation of the SCR. So this is the way we are able to protective measures we need to take. Another one is a gate protection of a thyristor. Why the gate protection is required? You can see that there is a like anode and cathode, we have as a circuit for gate and cathode. So we need to provide some mechanism to trigger the SCR. So what is that mechanism? Either you have to pass the current pass through the gate terminal. That current must be above the minimum and below the maximum. So that much current if we give gate and cathode, automatically the device is going to be fired. But once you are doing this mechanism, there also we need some protection. Or if you are passing high current, then what will happen? Power dissipation is taking place. Gate also terminal, there also having some resistance. So that leads as a problem. So gate power dissipation is also one of the problem. That's why we have to protect gate protection of the thyristor. Like a thyristor, gate circuit should also be protected from over voltages and over currents. Like device, anode and cathode, we are using that mechanism. Similarly, gate side also we need to see that it should not be more than the triggering voltage. There is a VGT is specified quantity. You can see that gate triggering voltage. VGT is nothing but a gate triggering voltage, or else IG minimum and IG maximum. IG minimum is a minimum gate current is required to trigger the device below the breakover voltage. Otherwise, if that IG minimum is equal to previous conduction value, then once IG minimum is below which, then the triggering voltage will be the same as the breakover voltage. So that phenomena we need to take care. So over voltage in the gate circuit can cause false triggering. Over voltage means what? It should not be beyond the VGT. No, VGT is required trigger voltage. VGT is a triggering voltage is required to fire the device. So whenever you require to fire, you have to pass VGT, or otherwise you can pass IG minimum. Any one you can use it to trigger it. But if this will be high beyond VGT, automatically device will trigger. it is unwanted. So that the problem, you can see that if you are not able to minimize that, then automatically there is a false triggering is going to be happen. So if you pass the current or voltage beyond the specified, automatically device is going to trigger. That we can the problem. And protective measures are what? Over voltage thyristor protection is achieved by using the zero linear diode, and the resistor can be used. What is the linear diode? That will clamp that voltage and will pass that. And some resistance also you can use it to minimize that what you call it as the current pass through that. So that way we can use it as a protection the gate circuit from the overcurrents. And the noise in gate circuit can also be caused false triggering or disturbance, or you can say that unwanted signal will pass through that leads as the triggering of the device also because of this noise, all these things in the or disturbance, or you can say that impure voltage and all can be avoided by using as a resistor and capacitor in parallel. So that means like a filter, nothing else. And diode D may be connected in series or in parallel with the gate to protect from the reverse voltages. So you should not pass the negative gate current. That is the reason gate current you must pass as a positive gate current. That's why source must be plus and minus and in series with the resistor, and it is connected to the what you call it as a protection mechanism. These are the another one. We can see that whatever we discussed so far, that we call it as a protective mechanisms in the previous class and today's class. And we'll move on to the series and parallel operation of SCR. So why we required series operation and why we required parallel operation? Anybody can respond this, because I told no, each topic I covered introduction. In all the 4 classes, each and every topic introduction I covered there. Now you should know why the series operation and why the parallel operation. Tell me anybody.
Sir, series operation is for voltage demand is high and parallel operation when current demand is high.
Yeah. So the thing is, each device we have the voltage rating and current rating. Let it be as a thyristor. It may be there 3 kilo amperes of current and 10 kV voltage like that, but not be fixed one. Whatever ratings you want, it will be available. So now for each device we have as a voltage rating and current rating, but the demand is more than one SCR rating. Then what we will do? One SCR cannot be meet your demand. Suppose our demand is some 100 kV line or whatever the controller you want to use it, but input is we can say that our SCR demand rating is only the, let assume that 10 kV SCR is available with you. Then what I have to do? I have to connect in series to get higher voltages. So that means we are forming as a string. So the string efficiency also very important. So that means to meet the voltage demand, we have to connect number of SCRs are in series. So they may ask in exam, if the string voltage is this one and available SCR rating is this one, then how many SCRs are connected in series. Similarly, the string current demand is known to you and one SCR current demand is known to you, current rating is known to you, then how many SCRs are in parallel to meet the demand? Like that they may ask your what you call it as a number of SCRs connected in series or number of SCR connected in parallel, like that, NS and NP, and that will purely depends upon your voltage ratings and current ratings. That is one aspect. And another aspect also, we need to find the string efficiency, what and device utilization also, utilization factor and all. So now the string efficiency means that actual voltage or current rating of the whole string. Here I am using as a both terminology, voltage and current, because whenever you want to find string efficiency for series operation, you can use voltage rating, and same formula only whenever you want to find the string efficiency when the CRs are in parallel or a current demand case, because parallel means current demand. In that case, you can use as a current rating. That's why in the statement I mentioned string efficiency is equal to voltage or current rating of the whole string. There is a voltage or current rating of the whole string. This is a not individual, whole string, divided by number of SCRs are connected in series or in parallel. Why I am using 2? If I use voltage here, then series operation you can use it. If I use current here, then you can use number of parallel. SCRs are in parallel into, this is a number, into 1 SCR voltage or current rating. So that means wherever if you want to find the string efficiency in the case of SCRs are in parallel, you can use this formula, actual current rating of the whole string divided by number of SCRs are in parallel into 1 SCR current rating, like that. So if it is series case, voltage rating of the whole string divided by number of SCRs are in series into 1 SCR is 1 SCR rating of the voltage rating of the SCR. So like that. So this is the string efficiency calculation. So now there is another term, there is derating factor. That means 1 minus string efficiency. So using this, we are able to find either string efficiency can find if they give number of SCRs are in series or in parallel, you can find easily string efficiency. Maximum cases what they may ask is how many SCRs need to connected in series or need to connected in parallel if derating factor is equal to some 0.1 or 0.2, like that. So because this utilization of the device means if you want more reliable, then utilization will be less. The reliability term is here. Some cases what we'll do is even though 10 SCRs are sufficient, I will use 12 SCRs or 13 SCR. Then what will happen? You are investing more because we are using more number of devices rather than your requirement, but reliability will be more. The reason is chance of failures are less. Instead of instead of doing 10 members work, if somebody is doing 12 batch, and if you do, then sharing of work will be minimum. I mean less work you can able to do. Then if it is less work, then the failure will be the less. Like that SCR, instead of 10 amperes current, if you carry only sharing only 5 amperes or 6 amperes, then it won't happen anything. The device will operate properly. So that means based on your requirement also number of devices is going to be changed. Not only voltage rating and voltage demand and current demand, but depends on your requirement. But to meet our voltage and current demand is very comfortably or minimizing the failure case, then you are giving more and more devices. So that way we can able to make use of that. We can reduce the reliability or increase the reliability based on this formula. You can see that derating factor is equal to 1 minus string efficiency. Once if you know string efficiency, some cases what they ask is if derating factor is 0.1, how many SCRs are connected in series and parallel. You can see derating factor is 0.1, and string efficiency also they may give sometimes that is equal to some 80%, something like that. Then how many SCRs need to connected in series if string voltage is or a whole string voltage is something 100 volts, let us assume that, and one SCR rating is equal to some 10 volts. or kV, whatever we want to use it, just for example. And what is how many number of SCRs need to connected in parallel or in series, because if the voltage demand string is given as a voltage, that's why you can use as a series operation. So now we can easily find derating factor is 0.1, that is equal to 1 minus what is the string efficiency is given here. You can use this formula, and here first you find the string efficiency is 0.8, that is equal to, you can use the voltage rating directly, will get it here. In some cases string efficiency also not given, only derating factor is given, directly we can use this data and you can find what is the number of SCRs are in parallel or in series, depends on voltage means series. So now derating factor and 1 minus string efficiency formula, whole string voltage is 100 divided by, you don't know how many SCRs are in series, into 1 SCR voltage rating is 10. Then what I can get here, if I solve this, I can get number of SCRs are in series. Similarly, current rating is given, suppose total string current is 50 amperes or 50 kV, whatever value. So 50 amperes is your total current, and the input side or string is 50 amperes is our requirement, the demand. But what is the 1 SCR current rating? Let it be as a 1 ampere or a 2 ampere or a 4 ampere, that also we know that. So 1 ampere rating, I mean 1 SCR current rating is known to you, total string is known to you, how many SCRs are in parallel. Then you can use the formula, in same formula, whether the derating factor is again 0.1, use the derating factor 1 minus string efficiency, and current rating is something whatever we mentioned 50, and here is 50 divided by n into 4. So that way you can able to find what is the series number of SCRs are in series and number of SCRs are in parallel. So that is the way we have to solve this problem. So now we can see that voltage and current ratings of 1 SCR 10 kV and 3 kilo amperes are available. Let it be, even nowadays more rating of the SCRs are also available. Let example I am telling 10 kV and 3 kilo amperes are available now. And some industry applications demand of the voltage and current ratings are higher. Then what is that? It may be higher than the single SCR, then it cannot be fulfill that. So that is the reason in such cases SCRs are connected in series in order to meet the voltage demand, and connected in parallel to meet the current demand. And the string efficiency is a term that is used for measuring the degree of utilization. So degree of utilization of SCR means that how best you are utilizing the devices. Some cases the devices are there but you are not utilizing full rating, then what will happen? You are not utilizing properly device, or rather otherwise you need only 10 SCRs in parallel, but if you connect 20 SCRs are in parallel, there also you are not utilizing properly full rating of the devices. So that will give string efficiency will give, if it is 100%, then automatically utilization also will be full. Then string efficiency of SCR can connected in series or in parallel. That's what the formula whatever I mentioned just before. Efficiency is equal to actual voltage or current rating of the whole string by individual voltage or current rating of one SCR into number of SCRs are connected in string, either it is in the series or in parallel. So both is given the formula. You want, you can separate it. String efficiency for series operation, then actual voltage rating of the whole string by individual voltage rating of one SCR into number of SCRs are in series. Similarly, if it is a current, you make use of string efficiency when the SCRs are in parallel, then you can see that actual current rating of the whole string by one SCR current rating into number of SCRs are in parallel. So like that you can modify your formula according to string efficiency. In practice this ratio is less than 1 because it is not properly utilized. That is the reason the ratio will be always less than 1. A higher possible of string efficiency, you can connect it in series or in parallel, must have the identical VI characteristics. That is very important here. Lot of problems will arise. How to overcome that problems, all these things we'll discuss in this area. So what it will do is, if both SCRs are not turn on at the same time, or turn on times are different, so if it happened like that, there is a lot of problem, because short circuit will occur, or string, total string also may damage due to this imbalance, or different turn on times or characteristics. So based on all the things we'll discuss in this operation itself, now must have identical characteristics, that is a identical VI characteristics. I will show that. If it differ, what will happen also. The same rating and same specifications do not have identical characteristics. So that is also the problem. There is a slight deviation if it there, that leads is a major problems. That also I will show you. If characteristics are different, what will happen the current sharing, or what will happen the voltage sharing. Let us assume that two SCRs are in parallel or two SCRs are in series. If the current sharing is not equal, then what mechanism we have to do it to make it as a same current sharing. Similarly, voltage sharing. That's the thing I am explaining here. Rating and specifications are same also. They may not be have as identical characteristics. Unequal VI sharing is, that leads what will happen, unequal voltage sharing or unequal current sharing will occur, and all the SCRs in a string that must be equal voltage sharing and equal current sharing we are expecting in generally, but due to characteristics of SCR, it is unable to share equally. There is slight difference will be there, but we need to overcome that things. So therefore, string efficiency may never be equal to 1. However, unequal VI sharing by the SCRs in a string can be minimized great extent by external equalizing circuit. The problem is identified. What is that problem? There is a chance of getting higher voltages in one SCR may share higher voltage, one SCR may share, I mean it is giving that sharing is less. So if that problem, or current wise also, one SCR will draw more current than other SCR. So all these problems we'll discuss in the next class. Anyhow, the continuation of this same series and parallel operation of SCR, it will take only 1 hour to complete this. We'll see in the next class. If you have any doubt, you can ask me. Otherwise, you can leave.